the last class, we already started so-called the partial differential equation. What is partial differential equation? So for simplicity, I will consider two independent variables, say x and y. Okay. So partial differential equation of say first order, it is of this form: f of x, y, then you depending on u, then the partial derivative ux, uy, this is equal to 0. Because I am considering first order, so this is first order PDE in two independent variables. X and y. Okay, so the unknown u is it should be a solution to your given PDE, and ux and uy, they are the partial derivative of the unknown function u. Okay, so I have given you example of semilinear PDE, linear PDE, quasi-linear PDE, and then the fully nonlinear PDE. So quasi-linear PDE means basically, if you look at the highest order, since it is a first order, the coefficients of your ux and uy, it depend on, in general, it is a function of x, y, and u. Okay, not is a function of ux. So it is something like that: a of x, y, u, ux plus b of x, y, u of uy, which is some c of x, y, and u for some function a, b, and c. Okay, these are the coefficient. So if you look at the coefficient, it depends on the lowest derivative of ux. Okay, so a, x, y, a is a function which depend on x, y, and u, and so on. Okay, so we'll study this kind of PDE. Then question is, what do you mean a solution to that PDE? So as a definition, I can say, like in your ODE. Also, I told you that ODE, because already we know that the solutions to your given ODE, if everything is fine, means the nonlinearity and so on, if it is ellipsis, at least local ellipsis, so that the solution exists and unique, then it depends on the initial condition. So you can think of UTX, the solution to your problem, say U prime t is equal to f of t of u with initial condition. So solution, if I write down u of tx, is it not? Because it depending on the initial condition. So if u is equal to x, I can write down this thing. So now this u prime t, I can think of dou dot t of utx, is it not? And that is actually equal to f of t u of tx. So my given ODE, one can view it as a PDE in this form. So what do you mean by the solution? Or I say that PDE is well posed. So PDE maybe I put as a star is well posed. What do you mean by that? That it has a solution. First condition is that it has a solution. Second is that the solution should be unique. And third condition is that if you vary the initial data or the given data, then the solution may not vary widely. So in the sense that solution depends continuously on the given data. Solution depends continuously on the given data. The same definitions, I think you have seen it for your ODE case, is it not? Okay, so here we try to solve a quasi-linear equation, that means in this form. Okay, and the initial curve is given to you, that I'll discuss later. So I try to solve it this PDE. Okay, and there is a well-known method that is called the method of characteristic. So basically what it says that I have now PDE, I try to reduce this to a system of ODE, and then you try to solve that system of ODE, and then you go back for your to the PDE case, because it reduces to a system of ODE. That is basically the method of characteristics, because we just try to find out that, okay, suppose my solution is constant along my characteristics or along some curve in R2, okay, and also it satisfies my PDE, then it reduces to solve a system of ODE. Okay, that is actually I'll try to write down. So before that, you consider this quasi-linear PDE, which is in this form: AUX plus BUY is equal to C, where A, B, C are function of X, Y, and U. Okay. So now what I am trying to, okay, everything is something like that. A, B, C, they are continuous. Okay. That is, you have to assume that. So assume that A, B, and C are continuous. Okay. So what I'm trying to say that suppose UXY, because it is two independent variable X and Y, this is a solution to star. Okay, given quasi-linear PDE. So, and I denote my Z, which is the graph of U. Z is equal to, okay, whenever I am saying that the graph, that means XY and then UXY. So I denote as Z is equal to U of XY as an independent in that sense. Okay, which is the graph of U. Okay, so suppose my Z0, which is the U of X0 and Y0, X0 and Y0 are given to you at some point, which lies in your R2, and I'm denoting Z0, which is U of X0 and Z0. So I denote this S, which is all those X, Y, Z, which is in R3, such that my Z is equal to U of XY. Is it not? Now you see that it is kind of the solution surface. Okay. So then normal to this surface, so normal to S, okay, at any point, say X0, Y0, and Z0, if I denote is N0, so then what will be my N0? Then N0 should be nothing but this is normal to surface U X of at point X0, Y0, U Y of X0, Y0, and then minus 1. So now, if I think of as a vector, say V0, which is nothing but my A of X0, Y0, and Z0, B of X0, Y0, and Z0, because A are function from R2 or in particular R3 to R, because X, Y, and then you have U, which is a real valued function. So now A gives you only real valued thing. So A X0, Y0, Z0, B X0, Y0, Z0, and C of X0, Y0, Z0. So this vector is perpendicular to the normal, is perpendicular to N0, and hence what
Excuse me,
happens?
sir.
Yes.
Hello.
Yes.
Sir, how did you get normal vector?
This one.
N0, N0. Yes.
Yeah. So what is the tangent to this case? Then actually it should be perpendicular to that things, no?
Yes.
So Z, this is a surface, no? Z is equal to U of XY. So tangent should be no UX UI. Is it not?
Yes, sir.
So see, you look at this is the surface, no? How do you find out the tangent? passing through the points x0, y0, and z0. So S is the surface. How it looks like? This is basically x, y, and then z point. This is the surface, no? Now you look at the tangent. So now I am considering the n0, which is this is the normal to that point. Okay. So that is how you have this part, no?
Okay, sir.
Okay. So now since A0, A, B, C, and you satisfy your given PDE, which is my star, this one. So from here actually what I can say that if you look at the tangent plane to the surface S at any point say x0, y0 and z0, then V0 which lies on the tangent plane, okay, perpendicular to N0, and hence V0 lies in the tangent plane to the surface S. Is it not? Okay. So now what is our aim? So here what I have seen that if my solution U is a solution to my given Cauchy linear PDE, which is AUX plus BUY is equal to C, and I am considering Z, which is the graph of my solution U, then what I consider, what I have seen here, that if you consider any point, say x0, y0, z0, and if you consider the v0, then there lies in the tangent plane to the surface S. Okay, this is for any point x0, y0, z0 I am having. So I want to find a surface. So looking at that, I want to find a surface say Z, which is equal to uxy, such that my vector field I denote as a vxyz, which is nothing but a of xyz, b of xyz, and c of xyz, which lies on the tangent plane to the surface S at any point xyz. Okay. So this is my aim. Just looking at point, any point x0, y0, z0, because here actually I'm saying that, okay, if my U is a solutions, then I am reducing in this point, or I am getting this point. Okay, getting this conclusion. So now looking at this conclusion, what I want, if my U would be a solution, then I want that, okay, say I want to find a surface which is something like z is equal to u of xy, such that if I consider my vectors field say v, x, y, z, which depending on my point, here you see that depending on your point, x0, y0, and z0, so that I consider as a of xyz, b of xyz, and c of xyz. Then from there what I have seen that if u is a solution, then it should be a surface. I want to find a solution. That means I want to find a surface z which is equal to u of xy, okay, to find z such that the vector field v lies on the tangent plane to the surface S. Already I have defined it S here. No? XYZ is equal to these things. So now this S is called, there is a particular name for this surface S, that is called the integral surface. So S is called integral surface. Okay. So that means to find a solution to this given problem, Cauchy linear problem, which is my a of ux plus b of u. Okay, a should I do a of x, y, and u, b of x, y, and u of uy. Then again, it is a function of x, y, no, ux. That is equal to c of x, y, and u. So to find a solution to this PDE, we need to find a surface Z is equal to U of xy such that my vector space Vxyz, which is A, B, and C, they should lie on the tangent plane to the surface S. Okay. So in particular, I think of as a Cauchy problem. So what do you mean by Cauchy problem? Means basically, suppose I know some level surface which is given to you, okay, on some curve. Okay, so this is my some curve, it is given to you, and here I know my solution, like in your initial conditions, no, it is given to you. So in this case, it is in two variables. So on some curve that I denote as a gamma, here my solutions I know it is given to you. Exyz is equal to h of xy, because as I told you that to find out solution to your PD, you need say initial or boundary conditions, or maybe both. Is it not? So here I am just giving you that I want to find a solution U which satisfy my Cauchy linear PDE. Okay. In what sense? Such that it is given to you that U of xy is equal to h of xy on some curve gamma, and I want to find a solution U such that it satisfy your Cauchy linear PDE in a neighborhood of gamma. In a neighborhood of gamma. Because if you think of in your differential equation, what do we have? That the solution exists locally in general, no? Then actually you are trying to find out whether the solution exists globally or not. So that means if you start with say T0, then you try to find out no T0 plus epsilon and then T0 minus epsilon in this neighborhood. So you have your T here in that neighborhood, solution exists or not. So now this is kind of things that gamma, which is the initial curve, it is given to you, and I want to know whether solution to this problem exists or not. That means we want to find a U such that it satisfies this equation, knowing that U of xy is equal to h of xy on gamma in a neighborhood of U. That means I can think of there exists a open set U such that, okay, U is subset of R3 such that A xyu ux plus B xyu uy is equal to C of xy u in U3, and it is given to you uxy is equal to h of xy on gamma, which is the initial curve. Okay, so as I told you that I try to use so-called the method of characteristics. That means we want to find a characteristic curve. So I try to reduce it to a system of ODE. Okay, and then if you have a system of ODE with some initial conditions, so then I can solve it using the picker types of technique or whatever you have done it for your ODE case. So for that, now suppose my initial curve gamma, it is given to you, gamma has a parameterization. Something like that. I have my Fs, G of S, and H of S. Okay, in R3. The initial curve gamma have a parameterization. That means X, Y, and then you have your Z, no? That is in R3. So I have a parameterization initial curve, which is I am denoting as F of S, G of S, and H of S. Okay, in general, I am considering, and then I need to find out the conditions F, G, H. H is given to you, which is here. Okay, so now for each S, I want to construct an integral surface which is parameterized by S and T. That means I want to find S, which is something like that X of ST, y of now s is fixed. No, this is the initial parameter. That's why s is fixed, and then I know that solution. Okay, so that is why I put as a t as a parameter again, y of st, and then I have z. No, that is my s. I wrote down z is equal to u of xy. So I put as a z of st for all t greater equal to 0. This is a my the integral surface s. I want to parameterize by s and t such that at t equal to 0, it should coincide with my initial parameterization. Is it not? That is how actually I want to do in a continuous fashion. Because this is my surface, I want to have solution or the integral surface for that. So now what I am doing, that I am parameterizing my initial curve, which is gamma. It is given to you by s, and then I am parameterizing the integral surface s by s and t. So that means if it is a solution to your problem, then at t is equal to 0, it should give back to your initial parameterization. That is actually I want to say that at t is equal to 0, at t is equal to 0, okay, we get say tau as a parameterized form. Okay, so now this ABC is perpendicular to the normal to your surface, is it not? So it should satisfy the following initial condition: dx dt, which is should be my a of no x of st. Okay, x means s and t, y of s and t, z of s and t. Similarly, dy dt, this is b of x of st, y of st, z of st. Okay, so I need initial condition. So now x of s of 0, this should be, as I said, that it should coincide with my initial parameterization at t is equal to 0. So initial parameterization is basically f of s. I am considering this is my f of s. Okay, so in this case, this is for y should be g of s, and then dz dt, this should be your c of x st, y of st, z of st, and then z of s0, this should be your h of s. Is it not? So now this PDE, the means we want to find this curve solving this system of ODE. So now since your A, B, C, it is given to you that it is continuous, we know that this system has a solution, is it not? By using Picard iteration or Peano's theorem, maybe you have seen it, that we don't need Lipschitz continuity, at least for existence result, I need means continuous is enough. Okay. So under certain assumptions on your condition, say A, B, and C, you can find out that for small t, is it no? For small t, that this system of ODE has a unique solution. Okay, and this curve which we are getting from here is called the characteristic curve. So now what we have to find the solution to your given quasi-linear PDE, we are reduces to a system of ODE. Okay, so that we can solve this system of ODE, that is basically along this curve. So this curve is called the characteristic curve. So now we want to find the surface in the xy variable, is it not? So now I have a solution which is x of st, y of st, z of st. But what I want a surface in x and y variable. Okay, so that means I need to invert my map xy to s and t, is it not? So for that case, what I need to use, we need to use the inverse function theorem. So now if you look at the near t is equal to 0, so what is the conditions of your inverse function theorem? See, I have the solution x which is depending on s and t. I have a solution y which is depending on s and t. So I want the inverse map, is it not? Because the surface in the variable x and y. So for that case, I need to use the inverse function theorem. So to apply that inverse function theorem, what I need to show that, okay, at least near t is equal to 0, if you look at the Jacobian, so which is x of s, y of s, x of t, and y of t. This is my Jacobian matrix. So now, if the determinant of this matrix, if it is non-zero at t is equal to 0, then I can use inverse function theorem that in a neighborhood, I can put it so that I can convert xy to s and t. So if this is not equal to 0 at t is equal to 0, then what I have, if you look at here, this is b of f prime s minus a of g prime s. This should be not equal to 0. Is it not? So now if I go back in the sense that if this condition is given to you, means if my gamma is given to you, means solution on gamma. So I want to find out my parameterization such that this holds, then I can use inverse function theorem and so on, and then I can find out my solution. So I need this condition to ensure the local existence of your solution. Okay, so this condition has a special name that is called the non-characteristic curve. So as a definition, what it says that a curve gamma is called non-characteristic if b of f prime s minus a of g prime s, this is not equal to 0. Is it not? So what do you mean by these things actually? So it eventually says that the tangent to gamma and the vector field which is ABC along gamma, if you try to project to the vector in the xy plane, then they are nowhere parallel. Is it not? Means they are perpendicular. They are nowhere parallel. That is how it means we have started that if u is a solution, then we have seen that at any point x0, y0, if you look at the vector space, the vector b, that should be perpendicular, means it lies in the tangent plane. Okay, so now here I have b and c. There is no way. That means actually you just project in the xy plane. So geometrically, what it says that the tangent to my surface, the curve gamma and the vector field ABC along gamma, if you project to the xy plane, they are nowhere parallel. Okay, so now if you go back here, that if I know that my curve gamma is non-characteristic, then I can find a unique solutions in a neighborhood of my gamma. So that I put as a theorem. So if this is not the case, then what is the problem that you may have non-unique, means solution may exist, but it may not be unique and so on. There will have infinitely many solution maybe. Okay, if the curve gamma is is characteristic of. So it is called non-characteristic if this condition holds, and in general it is a characteristic curve. Okay, so let gamma be a non-characteristic curve and A, B, C, they are say C1 functions. Then the Cauchy problem, what means this is A x y u ux plus b of x y u y c x y u in u. I'll say that what is your u, and then say u of x y. Yes.
Sir, I'm not able to understand the difference between characteristic and non-characteristic curve. Can you explain it once more?
No. What we are saying here, see, we want to solve this given Cauchy-Linear PD, this one, A x y u ux plus b x y u of uy is equal to c. Okay, and initial condition is given to you, u of x y is equal to h of x on some curve gamma. So now this gamma I am trying to parameterize, which I am denoting as fx g of s and h of s. Okay, this is the parameterization of your curve gamma in R3. Okay, see, gamma is something like that. Gamma is nothing but your x, y, and then u of xy, which is basically h of xy. I am parameterizing it via f of s. This is kind of your x, this is your y, and this is your z. Okay. Okay. So now I am also parameterizing my integral surface S, because already we have seen that if you want to find a solution to your Cauchy-Linear PDE, it is equivalent to find your integral surface S. That is why the previous discussion says.
Yes, sir.
Okay. So now I am considering my S, which is x of st, y of st, z of st. This is a parameters in both S and t, such that at t is equal to 0, it should be your initial curve. Is it not? Because if it is a solution, yes, then at t is equal to 0, it should give you the initial condition or the initial curve in this case. So that means at t is equal to 0, we get this gamma. Okay. So now what we have seen that the vector v, which is that ABC, this should be the tangent plane to your surface. Okay. So that means naturally I can consider that dx dt is equal to this equation, dy dt is equal to this equation, this equation, with initial condition this part, because it should be basically same for t is equal to 0, which is the initial parameters. Okay, so now suppose your a, b, c are say C1 function, so that you can use your Picard type of iteration to find out your unique solution for this system of ODE. Okay, which depends on S and T. So now I want to find out in terms of, because x and y, it should be your independent variable. So now whatever I have x of st. X is a function of s and t, y is a function of s and t. Okay, but I want only in the variable x and y. That means I need to invert the map, xy goes to s and t, is it not? Because it is implicitly given to you. X is a function of s and t, y is a function of s and t. So how that means I need to apply so-called the inverse function theorem, is it not? Because then actually you can write down that x as a function of s and t, y as a function of s and t, and so on, or vice versa. S can be write down as a function of x and y, t can be write down as a function of x and y, because I want in a only x and y. No, so that means I need to use the inverse function theorem. Okay, so to use inverse function theorem, what is the conditions you need? That okay, at some point the Jacobian matrix, it should be non-zero. Then in a neighborhood I can invert these things. So that is I try to say that at t is equal to 0, because I want to have a solutions nearby t is equal to 0, which is associated to your nearby or in a neighborhood of your given parameterization, given initial curve gamma. So that means I have x of s, y of s, x of t, y t not equal to 0 at t is equal to 0. So from there, what I am having, that B of f prime s minus A of g prime s, this is not equal to 0. Okay. So as long as I have these things,
Sir,
so this is
how you get this thing B of f prime s minus A of g prime s from the
at t is equal to 0, already we have this part, no? F of s, g of s, h of s.
Yes.
Is it not? So now you put
So
it here.
how do we get the prime then?
The derivative, that is why I know that a prime, g prime comes into picture. And also it should satisfy your initial condition, it is given to you.
Sir, how we are getting this thing from the determinant? Are we getting this from determinant or somewhere else?
This is the determinant, no? This is determinant, it should be non-zero. So this is xs y of t minus xt of ys. This is not equal to 0. Okay.
Yes.
So now what we know, that initial curve, it should satisfy. So what do I have? This x of s of t at t is equal to 0. This is f of s. So x of s I have. Okay. So at t is equal to 0, I have xs. So now it satisfies your initial also condition. So which is dx dt is equal to a at point x of 0. The initial condition I am having at t is equal to 0, and then dx dt, this is time derivative, which is basically x of t and y of t, which satisfy your ODE. Okay, this ODE. So that is why this coefficient a, b, c, and comes into picture. Okay, depending on the point. Okay, this b means basically this is a function, no? These things at put t is equal to 0.
So this determinant is not 0 at t is equal to 0.
Yeah.
So
that means this is same as my b of. Yes, tell me. See, what is xt? Xt is nothing but this part a. I can put it. This is a.
Yes, sir.
This is yt. This is b. I can put it here b. And x of s actually I just looking at from this initial condition at t is equal to 0.
But sir, you are placing f dash s. Means I'm not getting how this dash comes. F dash s
X
comes.
of s of 0 is equal to f of s. So this means basically x of s at s of 0 is equal to f prime of s, no? Or not? Is it clear? X of s0 is equal to f of s. So then dou s of x at s of 0 is equal to f prime s.
So this x of s represent a derivative. Then which derivative does it represent?
Yeah, this is the derivative, partial derivative.
So with respect to what?
This is x of s means with respect to s. This is y of t means with respect to t.
Oh, acha. Okay,
What you are thinking,
okay.
it is a dependent point or no? It is partial derivative.
I was thinking it's the point.
No. That's why I'm saying that x is a function of s and t. X is a function of s and t. Y is a function of s and t. And these are basically your, see, in your Jacobian things, no, what do you need? That the Jacobian matrix is the partial derivative things, no?
Yes, sir.
Yeah, that is actually I try to write down. And now if you just put it, this given equation and initial condition, exactly you have b of f prime s minus a of g prime s, which is not equal to 0. Okay, and I am saying that that is the definition. That means if you go back that I need these conditions, if you try to invert in the variable xy to t and s, I need these conditions at t is equal to 0, and hence the inverse function theorem that nearby t is equal to 0, you can invert it. So then if you do these things, I can have the integral surface s. Okay, so if you just go back, that is why I try to write down as a theorem form. So I need this condition to have unique solution. If gamma be a non-characteristic curve and the coefficient a, b, c are says at least c on function, then this Cauchy problem has a solution. Okay, in a neighborhood of your initial curve gamma, that is I put as a u. So u is nothing but the neighborhood of gamma. It's a open set in R3, neighborhood of gamma. Like no, in initial in ODE case, I have T0 minus epsilon to T0 plus epsilon. Okay, in that neighborhood actually I have a solution exists. So it is saying something like that. So in a neighborhood of gamma, x, y, z satisfy this condition, and z is equal to u of x, y. Okay, so let us consider one example, then it will be clear. So this method is called the method of characteristics. So basically what it says there, first you need to check whether, okay, first you need to parameterize your given initial curve gamma, and then you check whether it is a non-characteristic curve or not. If it is a non-characteristic curve, then you try to solve this system of ODE, which is given by this say maybe double star, and then you solve it x and t, x function of s and t, y and t, and we know that if this is non-characteristic, I can already convert it to x and y, and then you find that curve that gives you the solution to your Cauchy problem. Let us consider one example, then it will be clear. So suppose I am considering this condition, say ux plus 2 of uy, which is my u square. Okay, and h of, okay, u of say x and 0 is equal to my h of x, x is in R. So what is in this case my gamma, I can parameterize it, the parameterized form of gamma. This I can put as maybe s, then 0, there is no y component, and then I have, because y is 0, and then I can have maybe h of s. S is in my R. This is my initial condition. So that means in my general case, I wrote down this is f of s, g of s, and h of s. So f of s is equal to s in this case. G of s is equal to 0, and h of s it is there. Okay. So
Sir, this curve we have to find, or means it is given in the question.
no. See, u of x0 is equal to h of x is given to you.
Okay.
What is your gamma? This is a curve. Such on that curve, this is u of x0 is equal to what I wrote down, u of xy is equal to h of xy. It is given to you. So I want to parameterize my this curve. So that is I am wrote down. This is basically s0 h of s, such that s is exactly this parameterization of is your gamma, no? If s is in R, this is x0 and then h of x. That is my z, no? Which is equal to h of x, a0 h of s. So now you check that this curve is a non-characteristic curve. Okay, because you need to find out that Jacobian j, which is non-zero, so that, or whatever we know from here, no, directly I can think of b f prime s minus a g prime s. So g is equal to 0. Forget about that part. So now I have b f prime s. This is not equal to 0 or not. So f prime s is equal to f of s is equal to s. So f prime s is equal to 1. So that means whether my b is non-zero or not. So in this case, what is your b? So AUX plus BUI is equal to C. So B is equal to 2, which is non-zero. That means it is a non-characteristic curve. Is it not? Okay, or you can think of J is the Jacobian J is non-equal to 0, non-characteristic curve. So what is their characteristic equation now? That means the given ODE, system of ODE, we call the characteristic equation. So in this case, I can write down dx dt. This is A is actually 1. Is it not? With initial condition x of s and 0, that should be my f of s, which is s, and then dy dt, this should be b. B is in this case 2. And what is your initial condition? Y of s and 0, this should be 0 because that is g of s, so it is 0. Okay. And then what is my dz dt, which should be actually your c. Is it not? That is u, but u is equal to z, no? U of xy is equal to z. So that means dz dt is equal to z square, and z of s of 0, which is given to you h of s. Okay, so now we want to solve this system of ODE. Then how to find out? If you solve these things, we have that y, first from here, y is equal to 2t. No, 2t, and then constant is 0, so we have y is equal to tt. And then if you solve it from x, this is actually equal to t plus x. X is equal to t plus s. And then from here, this is dz by z square is equal to dt. And from you have this is 1 by z is equal to t minus, and that if you just look at the initial condition, this should be 1 by h of s, because at z of s0 is equal to h of s. Okay, so now if you solving this, means if you try to invert these things, inverting this variable, what I have, that t, which is my y by 2, and then s should be x minus y by 2, and hence I try to put it my t and s in this variable. Then what I have, my z from 3, this third equation, z should be your h of s, because from here what I have basically minus 1 by z is equal to t hs minus 1 by h of s, and z is equal to hs by 1 minus ths. So hs by 1 minus t of hs, and then I try to write down s there, because s is equal to x minus y by 2. So what I have, y is equal to, from here, now z is nothing but my u of xy, is it not? That is why we said that z is basically the graph of your solution u xy. So then u of xy, it should be h of s is nothing but x minus y by 2 divided by 1 minus t is y by 2. So t is y by 2, y by 2 of h of x minus y by 2. Okay, so now which is defined if this should be non-zero? Up to 1 minus y by 2 h of x minus y by 2, this is not equal to 0. Okay, so the solution to given PDE with initial condition, it is given to you that, where it is, yeah, u of x0 is equal to h of x, which is given by this form, u of xy, which is equal to h of x minus y by 2 by 1 minus y by 2 times h of x minus y by 2, and this is defined up to this case that 1 minus y by 2 times h of x minus y by 2 not equal to 0. Okay. Okay, so I'll consider one more example where we'll see that it may have infinitely many solutions. Okay. And then I will stop it. So that is called the characteristic problem, because for non-characteristic problem, what we are saying that it has a unique solution. No, uniqueness gives you because of you can uniquely convert it using your inverse function theorem. So now I consider this problem ux plus uy is equal to 0, where xy is in my R2, and then u is equal to h on gamma. Okay, gamma, it is not, I'll find out that if gamma is something, then you end up with unique solutions. If gamma is another thing, you end up with non-unique solution. Okay, so depending on your initial curve. So I'm saying that now suppose my gamma is non-parallel to y is equal to x. Okay. So suppose gamma is something like that. I can think of on gamma where my solution h xx form. Okay, that is equal to h of x, means I can think of u of xxx is equal to h of x. Okay, for this problem. On for x is positive, I can think of x is in R, so that u of x is equal to h of x. So that means in this case, what is my parametrizations of gamma? That means basically this gamma is parallel to y equal to x. So then the initial parametrization for my gamma in this case, which is s, s and h of s. This is no parametrization. So initially I am saying that okay, I have arbitrary gamma, but I try to impose on gamma how, so that I may have unique solutions, I may have non-unique solution. So for the first case, I'm considering say gamma which is of this form, means initial condition is given to you something like that, u of xx is equal to h of x. Okay. So in that case, what you have, so f of s is equal to s, g of s is equal to s, hence f prime s is equal to 1 is equal to g prime of s, and in this case a is equal to b is equal to 1 and c is equal to 0. Is it no? The given PDE. So what you have, that bf prime s minus a g prime s, that is actually is equal to 0. Hence the Jacobian is 0. So if the Jacobian is 0, you cannot say that it has a unique solution. So therefore, the solution exists uniquely if gamma is not parallel to y is equal to x. So what I try to say is the following. So in this case, if it is parallel to y equal to x, I'm considering this one, no? U of xx is equal to h of x, which is, that means my gamma is parallel to y is equal to x. Okay. So if it is parallel to y is equal to x, I cannot say that it has unique solution. Is it not? Because my Jacobian j, this is 0 in this case. So that is why I'm saying that therefore the solution exists uniquely if gamma is not parallel to y is equal to x. So this is not related to now this one, this condition. What I try to say that suppose it is parallel to y is equal to x, then the initial curve exactly like this. And then I can say that Jacobian j is equal to 0. So in this case, it does not have unique solution. Okay. So I try to say that for this case, whenever u xx is equal to say h of x, I can solve my problem, say u of x of 0 is equal to my h bar of x. Okay, I am considering my another problem with initial condition, which is again same x, ux plus uy is equal to 0 and u of x of 0 is equal to h bar of x. I will define later what is my h bar, what is the relation between h bar and my given h. Okay. So then if you solve this characteristic equation, then what I have, and h bar is such that this is, in this case, if I put u of x0 is equal to h bar of x, you see that if you consider the, say, gamma bar may be initial curve in this case, this is non-characteristic. So I can have a unique solution in this problem. So then the solution to this, if you consider the characteristic equation associated to this problem, then what I have, dx dt, which should be your 1, dy dt, it should be again 1. Okay, with initial condition you have x of s of 0, this should be your s, and y of s of 0 should be 0, and then dz dt, this is actually 0, and z of s of 0 is equal to h bar of s you have. Is it not? So from here what I have, since dz is equal to 0, so I have a z is equal to my nothing but h bar of s, z of ts, which is h bar of s, and from here what I have, x is equal to, from here, t plus s, from here I have y is equal to t. Hence my solution looks like x of y, which is h bar of x minus y. So therefore, on y is equal to x, what I have, u of xx is equal to my h bar of 0. Okay, so that means if u, which is a solution to your underlying problem, then necessarily it should satisfy that h of x is equal to h bar of 0. Is it not? If you use a solution to your given problem with this condition, u of xx is equal to h of x, so then what it says that it should necessarily satisfy h of x is equal to my h bar of 0. Is it not? That is, h should be constant. That means my h should be constant. So in this case, we have infinitely many solutions. In particular, I can think of u of xy, which is equal to c plus h tilde of x minus y, with h tilde 0 is equal to 0. Okay, so you see that these things satisfy your given PDE. Ux plus uy is equal to 0, where and u of xx is equal to h of x. Okay, so for this is called the characteristic problem, because here Jacobian j is equal to 0. So this is a particular example I am saying. So in general, if Jacobian j is equal to 0, we cannot say that it has a unique solutions. But whenever it is a non-characteristic, so the theorem says that it has a unique solution. Okay, I'll stop now.